Plate tectonics. When viewing Earth from space, you may think that continents and oceans have always looked as they do now. You probably have looked at a globe many times and know the names, shapes, and locations of all the continents as they appear on Earth today. Can you name all the continents? Do you think the continents looked the same way 200 million years ago? Let's see what happens when we go back 200 million years in time. And let's look at how the continents moved over the last 200 million years. Let's look at that again from a different perspective. The movement of the continents that resulted in the formation and breaking apart of Pangaea occurred during the Paleozoic, Mesozoic, and Cenozoic eras. Many common features like rivers, mountains, lakes, and islands may not have existed at all. 200 million years ago, there was no Grand Canyon or Rocky Mountains. The age of the Colorado River is still in debate, but it is generally believed to have begun sculpting the Grand Canyon anywhere from 6 million to about 17 million years ago. The Grand Canyon is 445 kilometers or 278 miles long, extending from Lake Powell on the east to Lake Mead on its west end. The Rocky Mountains formed between 75 and 50 million years ago when the ancient Farallon Plate slid under the North American Plate, uplifting Earth's crust in an event called the Laramide orogeny. In 1915, Alfred Wegener, a German geophysicist and meteorologist, developed the continental drift hypothesis. He proposed that the continents had once been joined as a supercontinent, which he named Pangaea, or all lands. Pangaea began to break apart about 200 million years ago, and the fragments drifted over time to their present positions. Look at this movie carefully. You may notice that some large land masses split apart, while in other areas the oceans closed. Some smaller land masses that were originally separated crashed into one another and formed larger continents. Continents are still changing today. Their continual movement causes geological phenomena such as earthquakes. A 7.1 magnitude earthquake occurred near Loma Prieta in the Santa Cruz Mountains, California, on October 17, 1989 at 5:04 p.m. Pacific Daylight Time. It caused severe damage in Oakland and San Francisco, including this collapsed building in the Marina District. The first and second floors of this three-story structure collapsed, leaving only the third story. The second photo shows the support column failure and collapse of the upper deck of the Cypress Viaduct in Oakland, California. Volcanoes also commonly occur on Earth. Mount Etna is one of the most active volcanoes in the world. This video shows an eruption consisting mostly of volcanic bombs, cinder, and glassy ash. The movement of Earth's continents also produces Earth's majestic mountain ranges. One example is the Himalayas. View of Everest from the Kala Patthar. What causes volcanism, earthquakes, and mountain building? The underlying cause is plate tectonics. What is plate tectonics? Plate tectonics is a theory that states that Earth's outer shell consists of a patchwork of pieces called lithospheric plates, or plates. Plates are in a constant state of motion. Some move away from each other and some move towards one another. Let's assemble these puzzle pieces that make up the Earth's plates. You may need to go back and rewind this video to see the number of puzzle pieces that make up the Atlantic Ocean. In this app, you will discover how the interactions of Earth's plates cause various geological occurrences across the globe, like earthquakes, mountains, and volcanoes. The earthquake was in Haiti. The mountains shown are the Alps, the highest mountain range in Europe. The Eyjafjallajökull volcano in southern Iceland erupting is shown last. After several decades of intense oceanic exploration, a better picture of the seafloor emerged. It was found that new oceanic lithosphere forms at the oceanic ridge where hot magma oozes up from the mantle below and spreads outward. This mechanism was named seafloor spreading. As lava at the oceanic ridge cools into rock, it becomes magnetized parallel to Earth's magnetic field. The magnetic field pointing to the magnetic north pole is normal polarity. During a magnetic reversal, it changes direction and points to the magnetic south pole, called reverse polarity. In the mid-1960s, a number of magnetic surveys performed along oceanic ridges of the Atlantic, Pacific, and Indian Oceans showed zebra-stripe patterns of alternating strips of rock with normal and reverse polarity parallel to and mirrored on both sides of an oceanic ridge. Researchers were able to correlate the dates of pole reversals on the spreading seafloor to determine the floor's age and the speed at which it was spreading. Other important discoveries were also made. The age of the oceanic crust was youngest near the oceanic ridges and oldest, not more than 180 million years, farthest from the ridge. Sediment accumulations on the ocean floor were thin, not thick as originally thought. Earthquakes were occurring below deep ocean trenches and along oceanic ridges. By 1968, this knowledge of the ocean floor led to a new, more encompassing theory than the continental drift hypothesis known as the theory of plate tectonics. According to the plate tectonics model, Earth's crust and uppermost mantle makes up a cool, rocky layer called the lithosphere. The strong, rigid layer is thinnest in the oceans, where it varies from only several kilometers at the oceanic ridge to about 100 kilometers or 60 miles in the deep ocean basins. It is made of basalt, a rock rich in dense iron and magnesium. The much older continental lithosphere, as much as 4 billion years old, averages about 150 kilometers or 90 miles thick, but can extend to depths of 200 kilometers or 125 miles or more beneath the oldest portions of the continents. It is composed mainly of less dense granitic rocks. Below the lithosphere is the asthenosphere, a hotter, weaker layer in the mantle. Pressure and heat bring the rock in the upper asthenosphere near to melting. The rock is mainly solid but is capable of flow. The cooler lithosphere can bend or break but not flow, which allows it to move separately from the weak rock in the asthenosphere. The lithosphere is fractured into curved segments called lithospheric plates or plates. Each plate contains either oceanic crust or continental crust. Some plates comprise various combinations of both types of crust. 7 major plates are recognized and cover 94% of the Earth's surface. They are the South American, North American, Pacific, Australian Indian, Antarctic, Eurasian, and African plates. The Pacific plate is the largest, encompassing almost the entire Pacific Ocean basin. Most of the major plates contain both a continental crust, and a large portion of ocean floor, oceanic crust. There are 7 intermediate-sized plates. They are named the Philippine, Arabian, Scotia, Philippine, Arabian, Scotia, Caribbean, Nazca, Cocos, and Juan de Fuca plates. Most of these plates contain mainly oceanic crust. There are a number of minor plates in addition to the ones mentioned here. Each plate moves as a rigid unit is in constant motion. Study this map to see how plates move relative to other plates. As the plates move, the distance between Denver and New York on the same plate remains constant, while the distance between the cities New York and London on 2 different plates gradually changes. Because the plate boundaries are constantly changing, most geologic interactions occur along their boundaries. Most earthquakes, volcanoes, and mountain building are found along the margins or edges of the plates. You can see another photo of the Cypress Viaduct in Oakland from the Loma Prieta earthquake. Most earthquakes are distributed at the plate boundaries. In fact, most plate boundaries were determined by plotting the locations of earthquakes and volcanoes. Notice how many volcanoes are also found near plate boundaries. The world's mountain belts are also associated with plate boundaries. There are 3 types of plate boundaries: divergent, convergent, and transform plate boundaries. Divergent plate boundaries occur when 2 plates move away from each other. These plates have constructive plate margins where new ocean floor is generated, often along oceanic ridges. This is a divergent plate boundary where new magma rises from the mantle and cools into new oceanic lithosphere. This type of boundary can cause earthquakes. 2 plates move toward each other at convergent plate boundaries. These plates have destructive plate margins where ocean floor is being destroyed as the older, denser oceanic lithosphere descends into the mantle. The leading edge of one plate is bent downward as it slides beneath the other. This is a convergent plate boundary where oceanic lithosphere subducts or slides beneath continental lithosphere. Note the features present at this type of boundary. Transform plate boundaries, or transform faults, occur where 2 plates slide horizontally past each other. This type of fault does not create or destroy lithosphere. Some transform plate boundaries are found on land. Transform faults allow plates to slide past each other, cutting through continental crust. Note the offset stream. All 3 types of boundaries can be found surrounding some plates. An example of this exists at the margins of the Juan de Fuca plate off the northwest coast of North America. The Juan de Fuca has divergent boundaries on the west, shown in red. A convergent boundary is found on the east, shown in black. Numerous transform faults join segments of the divergent boundary and run along the coast, shown in blue. When the plate tectonics theory was accepted, We now know that the continuously changing patchwork of lithospheric plates is the cause of the movement of continents and ocean floor basins. As a result, many of the world's earthquakes, volcanoes, and mountains are produced because of these dynamic forces.